For the following problems, we want to know, is the following series geometric? If so, find the common ratio and the first term. To determine if a series is geometric, we would need the general term to be able to be rewritten to have the form AR to the n. So some we might be able to just look at to determine that this is geometric, or we might have to do a little bit of work to rewrite it to see, can it for sure be written in this form? So here, the sum of n equals 0 to infinity of 2/5 to the 2n. So here, yeah, we can do a little bit of rewriting. So we could write the sum of n equals 0 to infinity of 2/5 squared to the n. So basically we can square 2/5, so that would be 4 over 25 to the n. And so this is exactly now in the form AR to the n. So yes, this is geometric. So in answer to this question, yes, it is geometric. And now we're going to find the common ratio and the first term. So the common ratio is the value that's raised to the positive n. So the common ratio, R, is 4 over 25. Now, the first term can always be found on any series by substituting in the starting index value. So if I substitute in 0 into the general term, what's the first value that comes out? 4 over 25 to the 0, anything to the 0 is 1. So the starting term here is 1. Now we have the infinite series, the sum of n equals 1 to infinity of -1 over 2n. So in order to be geometric, we have to have something that looks exponential in form. So here, 2n is not exponential. I don't see a number in the base and an n in the exponent. So is the following series geometric? The answer here is no. We do not have, it's not geometric. Don't have a geometric series. So there is no common ratio. So we won't move forward with, if so, find the common ratio and first term. Here we have the sum of n equals 0 to infinity of 3 to the n minus 1 over -2, all raised to the 2n. So here, can we rewrite this so it looks like AR to the n? Well, at least we have some exponentials. So we have a number in the base here and n up in the exponent, a number in the base, something involving n in the exponent. So let's start to try to rewrite this. So we'll write the sum of n equals 0 to infinity. So what I'm going to do on this one is I'm going to write this as 3 to the n times 3 to the -1. And then on the bottom, -2 to the 2n. So I'm going to take -2 and square it. So that's going to be 4 to the n. Okay, so now 3 to the -1, I can move that to the other side of the fraction bar, and that would make this a +1. So I'm going to have the sum of n equals 0 to infinity. I would have 3 to the +1 in the denominator. And 3 to the n on the top still, and 4 to the n in the denominator. So since these have the same exponent n, I can bring this back together as 3/4 to the n. So I have n equals 0 to infinity of 1/3 times 3/4 to the n. So I did definitely a lot of work just to really show where this is coming from, but I do have AR to the n. So this is geometric. So yes, this is geometric. And the common ratio is what is raised to the n power. So we have 3/4. And the first term, again, can always be found by substituting in the starting index into n. So 3/4 to the 0 is 1, but there's this 1/3 in front, so the first term is 1/3. Here we have the sum of n equals 1 to infinity of n factorial over pi to the n. So that n factorial really automatically tells us that we do not have a geometric series, even though pi to the n, that piece is exponential, so I have a number pi in the base and n in the exponent, that part, you know, leads me to think about a geometric series, but it can't have the n factorial there. So for that reason, this is not geometric, and we don't need to do anything else. Here we have the sum of n equals 1 to infinity of 0.3 to the n plus 1. So here, what I can do is, decimals are fine, but if I prefer fractions, I can rewrite 0.3 as 3/10. So I have 3/10 to the n plus 1. And what I could do is I could split this up as the sum of n equals 1 to infinity of 3/10 to the n times 3/10 to the 1. So it's flipped, but this is ar to the n. So my r value is 3/10, so this is geometric. So yes, this is a geometric series. R is 3/10. And now let's think about what happens when I substitute in 1 into my n. So if I substitute in 1, I'm going to get 3/10, but there's this other 3/10 here. So that's going to end up being 9 in the numerator, and then 10 times 10 is 100 in the denominator. So my a1, my first term, is 9 over 100. I should kind of stay similar. I'm going to write my fractions as a clear numerator over denominator. So my r is 3 over 10. My first term is 9 over 100. And last one, n equals 0 to infinity. We have 5 to the 2n minus 2 over 2 to the 3n plus 2. So this does have, you know, my number in the base of each, the numerator and denominator, and variables in the exponent. So we just want to manipulate this a little bit so it looks like that ar to the n. So let's start by saying n equals 0 to infinity. We have 5 to the 2n times 5 to the negative 2 over 2 to the 3n times 2 squared. Okay, so now let's see what we can do from here. The sum of n equals 0 to infinity of, so 5 squared, that's 25. So what we have is 25 to the n. I'm going to work down here. 2 cubed, that's 8. So this is 8 to the n. I have 2 squared in the denominator, that's 4. And then 5 to the negative 2. So I want to bring that factor to the denominator and make it 5 to the positive 2. So times 5 squared, which is 25. And so these two have an exponent of n now, so we can bring those together. So let's see what we get. I'm going to combine a bunch of things at once here, let's do 25 over 8 to the n, so that's working on these two. And then I would have in the front there 1 over 100. So 5 squared is 25. 25 times 4 is 100. It's in the denominator, so 1 over 100. And then 25 over 8 to the n. So yes, this is geometric. Just took a little bit more algebra than usual. R is 25 over 8. And now let's wrap up with the first term. So the first term, if I substitute in 0 into n, anything to the 0 is 1. So we just have 1 times 1 over 100. So we have our first term.